So here we see a very educational problem that should help us to grasp the concept a little bit better and in more detail. So let's first examine the problem and understand what's going on. So number one, we have to find X bar and Y bar. That's our task here. And we already see here that it is a composite shape. And the composite shape here is no secret, is really three shapes. Let me section that for you. So I effectively have the triangle, the rectangle, and then let me explain to you that this circle here represents a hole. I hope that's obvious from the picture, but if not, let me tell you, this is a hole. So therefore, again, educational problem, it will teach us what to do with negative areas. And of course, in reality, negative areas don't exist, but a hole can be subtracted. But I will show that to you as we go through this problem now. So let's remember that our formulas again was X bar is equal to the summation of X tilde I times AI, and the whole thing divided by the summation of AIs. And just for my reference, I also write down my Y formula because I will need that as well. And this is very similar. Summation AI. So the first thing I now need to do is identify my individual shapes, my defined known shapes. And in this case, I will make my life easy, and I know that I have a triangle here, so I'm going to call that here shape number 1. And then I have a rectangle here, I'm going to call that shape number 2. And then last but not least, I have my shape number 3, which is the area of the circle, which is a hole, right? So I will have to subtract that. So now all I would have to do is identify each of these elements for my individual shapes and then sum them correctly. So let's, for an example, talk about this first shape here, the triangle. I can clearly find X tilde I can find AI, and I can find the contribution to the total area. Let me tell you before I start this problem that if you find other methods online or other teachers, they will probably teach you this with like a tabularized method. I will show you later how that works as well. But I find that always a little bit risky. In fact, I have seen students who just want to follow a recipe instead of following the logic of the problem. So I think that's not a good first step to learn. Like if I show you the table and you just want to fill in the blanks, it's not conducive towards you understanding the problem. So let's, for this problem, not use the table method. I will explain that to you later, but let's instead just focus on the individual elements. So let's get started by looking at our individual shapes here. For example, shape number 1 has a centroid location roughly at this location. Shape number 2 and 3 share a centroid location right there. So the first thing I'm going to do now is identify these in my sketch for our very first educational problem here. Remember that we always do it in reference to the coordinate direction. So this here would be X tilde 1, which in this case happens to be 2/3 of 300. So that would be that distance. And then the next X tilde 2 and 3 would be the distance from here to here. So that would be X tilde 2, which is equal to X tilde 3 in this case, which is equal to 300 plus 150. We can continue with that and work on our Y tilde directly. So let's do that. So our Y tildes are directed along the vertical axis. So I have the first one here and then the second one here. And if I bring that over from here, then I have these distances and of course the x-axis. So let me zoom in. This here would be Y tilde 1 and this would be Y tilde 2, which also happens to be Y tilde 3. Since I don't have much room down there, I will now write that down here. Y tilde 1 is equal to the height times 1/3, so that's 200 times 1/3. third, and y tilde 2 is equal to y tilde 3, which is equal to 1/2 of 200, which is actually also shown to you right here. And now I have to find my areas, so let's do that. So my area for shape number 1 is 1/2 times base times height, right? So A1 is equal to 1/2 times base, which is 300 times 200, which is the height. And that results in 30,000 millimeters square. Strange large numbers here, right? But the millimeters are so small. So now we can do A2, which happens to be 300 in width times 200 in height, which is twice the area of the previous one, which happens to be 60,000 millimeters squared. And now be careful, because A3 is really a negative area because it's our hole. So pi r squared would be 75 squared. And that is a negative area of 17,671.5 technically millimeter squared. And now I almost have everything I need. Just for completeness reasons, I'm going to give myself here the little input or the little help. I didn't calculate those earlier, so I'm going to include that this is 200, this is 450 millimeters. Just so it's easier for me to use that in the formula later on. And then up here, I kind of forgot that as well. So my y tilde 1 was 66.66 or 67. And my y tilde 2 was equal to 100. And of course, those are also in millimeters. And now I have everything I need to complete these formulas here on the top right. I have my AIs, I have my X tilde I's, and I have my Y tilde I's. Maybe for completeness reasons, we will add now that the total area here is equal to A1 plus A2 plus A3, which in our case happens to be equal to 72,328.5 millimeters square. So that's the entire area content of that shape. And now all I have to do is use these formulas here. So let's start with X bar. I'm going to find that for you first. So X bar happens to be X tilde 1. How much was that? That was 200 millimeters. And then I multiply that by the area, which is 30,000 millimeters squared. And then it's a summation. So now I'm going to add to that the X tilde 2, which was equal to 450 millimeters. And I multiply that by the area, which was 60,000 millimeters squared. And now comes the tricky part, because now comes the negative portion, and that is both the area and the lever arm, if you want to call it that way, or the distance. So I'm going to subtract the entire thing, which was equal to 450 millimeters. And the area in this case was 17,671.5 millimeters square. And that now is everything I need for that portion. Now I have to divide it by the total area. So let's put in the division bar here. And now I divide it by the total area, which is 72,328.5 2,328.5 millimeters squared. And the first observation that I can make is that I have millimeter to the 3 divided by millimeter squared. And that is good because that means that I end up with millimeters. And that is what I want. In fact, the solution, the numerical solution to this is 346.3 millimeters. And that is a result, so I'm double underlining it. And of course my units belong in square brackets. And now let's take a look at the picture. Is this number meaningful, or does it make sense in the content of this picture? And I think it does, because 346 is beyond this triangle to the right, but not half of the rectangle. So let me explain that in other words. If I were to have a rectangular block that was completed like this, no triangle here, no circle taken away, then we would know from the very beginning that our centroid would be here. However, we removed a triangular portion here. That means our centroid location would move to the right. And then we removed the circle, which means our centroid location moves a little bit back to the left. And so the 346.3 does make sense. In fact, for full points on my exam, I would have to include that in my sketch. And so the first thing, of course, it has to be symbolic, but you have to show that you can see the difference between X bar and Y bar. So I first will draw this line here, and I'm going to call this now X bar, this distance from here to here. So let's call this here X bar, which is equal to 346.3 millimeters. And I show that I understand where that centroid location is. And by the way, something similar is true for Y bar. So if we had a complete area here, then Y bar was exactly half of 200, so it needs to be less than 200, right? And however, we're also removing this, so we'll see if this area has a bigger contribution than this, but it should be somewhere between the middle and this point. So we will calculate that next. In fact, let's do that. Let's calculate our Y bar. So let's calculate Y bar, which now would be Y tilde 1, which was equal to 66.67, so that you see where it's coming from. Let me zoom out a little bit. And then multiply it by the 30,000. And you notice I don't use units here right now, just to save you some time. Now my Y tilde 2 was equal to 100. And I multiply that by 60,000. And then again negative 100 multiplied by the very same area, 17671.5. And of course, to no surprise, my total area did not change. So I can just divide everything by 72,328.5. And this comes out to be 86.18 millimeters. And does this make sense? I think it absolutely does, because if we look at the picture here, the 86 is definitely below the half of the shape. And so I can now include that in my picture up here. So let's say that this here is the location. And so this distance to here, maybe I should show it on the other side because it's easier to observe. So the distance here would be Y bar, and that is 86.18 millimeters. And so now I clearly showed in my sketch the difference between X bar and Y bar, and it also shows that I understand that the centroid location is right here. In fact, I probably should make that even more clear. I should say that here is my centroid location. So this is the centroid location. And with that said, I think we solved the entire problem. Here's everything at one view. Important for us to understand here is that we know how to use every individual component in these equations, which I believe I showed you here. And then solving everything below here is just plug and chuck. Once you understand where each component comes from, then you can just blindly follow these equations. The last important thing then is that you clearly show where the centroid location is, because it is my experience that often students can calculate these numbers correctly because they can plug and chuck well, but they cannot show where that is located on the actual sketch. And therefore it's very important to me that in your final answer sketch you actually include the location of the centroid, and you also clearly show what is Y bar and what is X bar. And when you do that, then you can get full points for this and you understand the complete topic. And that concludes this problem. Let's take a look at our next problems just for practice, for additional practice purposes. So here we have a problem for the centroid location with a fairly simple shape. So centroid location, again, we're trying to find X bar and Y bar. And this problem also gives me a good opportunity to talk to you about the reason for us as engineers to calculate these centroid locations. What you see here is a barrier, or like a traffic barrier. It could be something else, but let's just pretend for a second this is a traffic barrier. And this traffic barrier has a centroid location. And I'm just guesstimating right now. I'm saying that maybe it's somewhere here. Maybe it's actually within those triangles there below. But of course, there's then a centroid axis. So let me draw that into the problem here. That would be located somewhere along this axis. So that would be pretty much the centroid location. And if you now have a traffic approaching it from the side, you want to have it such that the actual car has the centroid location acting below the centroid. So if the car, and this here represents my car, it's a very poor car, I admit that, but just conceptually speaking, so if the car approaches this barrier from the side, it wants to cause this to tip over, and it is much more difficult for the barrier to tip over if the force of the car hits the barrier below the centroid location, because then it will just push it to the side, whereas if you hit it here on the top, you would actually tip it over. And of course, this is an educational problem, so in reality these dimensions are not like this. In fact, a traffic barrier of these dimensions would be completely useless, but I guess you get the point, right? So you need to be able as an engineer to calculate the location of the centroid so that you can plan, for example, traffic barriers properly and such. But for the purpose of this problem, I will now erase all these marks on here, and I will now show you how we can calculate such centroid locations for a fairly simple shape. In fact, let's talk about the shape first. Let me zoom in here. So I first, remember, have to discretize the shape into shapes of known geometry. And I could, for example, do it like this. So I have like a vertical component, and then I have this horizontal component on the bottom, which would run from here to here. And this would be an absolute fair way, or absolutely okay way to discretize this image. However, just to show you that there's also another way in this case, I will erase this now again, and I will show you that you will reach the same result if you discretize in a different way. And that could be, for example, like this, where the horizontal part on the bottom is continuous and the vertical component is not continuous anymore. And that is what I will use actually to now solve my problem. In fact, you can see now that I have this shape, let's call this here A1. So this here will be my A1. And then let's have a red shape A2, which would be this down here. So this would be A2. And then I have, I guess, what's called A3, area 3, but I'm going to call that area 3A, because on the other side I have area 3 as well. So this would be A3, but I'm going to call that B. And why do I differentiate those? Technically, if I was already experienced with this, I probably wouldn't have to do this, but just to get one point across here, I want to point out that the coordinate origin is here at the center of this shape. And so area A3B is to the right of that, and area 3A is to the left of it. And so one of them has to be negative, whereas the other one will be positive. And by that I mean actually the x tilde has to be negative. In fact, let's talk about the x tilde real quick. So remember that I have to calculate x bar here, and x bar is usually some formula, but in this case I really don't have to calculate that. It actually happens to be 0 due to symmetry. So you can see here that the y-axis is exactly halfway between shape A1, if you will, or in the middle of shape A1 and also in the middle of A2. And therefore I don't have to do any calculations. I know for a fact that because this cross-section is symmetric, that the centroid location must be located somewhere on the y-axis. The distance from the x-axis, which will be actually y bar, that I will have to calculate now. And I will have to find out how to do that. So I think we should get started on that. And as I promised you, I will do this now with the tabulated method. So, which again is not always a good way, but maybe we can use this to get ourselves familiarized with the tabulated method. So what do I need? Like our formulas, maybe I should write down the formula first. So the formulas that I usually have is the sum of y tilde I ai divided by the sum ai. And so I need to find certain things. I need to define ai, I need ai, y tilde I, and then a total, and then also the summation of that. So a standard table for problems like this that you often find in textbooks looks as follows. So first we have the shape, and then we have the area. And the area is in this case given an inch square. Then we have x tilde I, which is usually given in inch. And then we have y tilde I, which is also given in inch. And those are entities that I can pretty much read from the picture. So these are geometric properties. However, we also have the computational properties, if you will. And that, for example, would be x tilde I ai and y tilde I ai. But we'll talk about those in a little bit. However, so let's turn this into a table now. So I have my rows like that. And now I have to populate the table with 4 shapes, right? Remember, I have pretty much A1, I have A2, and I have A3A and A3B. And I will now consecutively go through those and explain to you where which value comes from. So the area for shape number 1 is fairly straightforward. And let me make sure that I keep the picture here for you visible. So the area A1 has a base times height of 1 inch multiplied by 7.5 inch, right? 7.5. And so that is 7.5 inch squared. Maybe I should put an equal sign here. Now, what is x tilde for that shape? So let's look at that. So x tilde is really the distance, remember, from the centroid location of the individual shape to the origin of the coordinate system. So I will zoom in now to give you a geometric reference here. So let's say I have a centroid location right here. And the first thing you see is that the centroid location of the shape A1 coincides with the y-axis. We talked about this before, but that means that I have a distance in the x direction, so of 0, which means that my x tilde will be 0. However, for the y direction, it's a little bit different and a little bit tricky, so I will give you references for those as well. So let's say I want to know from this location here. So from here to here. And that distance would be 7.5 divided by 2. So 7.5 divided by 2. Why 7.5 divided by 2? A lot of students would have taken 6 divided by 2, but keep in mind that your cross-section actually goes all the way down to here, which includes the 1.5. 1.5 plus 6 is 7.5, and divided by 2 because we're looking at a rectangle. So this distance must be 7.2 divided by 7.5 divided by 2, sorry. And so, but the distance that's even more interesting for us is the one here on the bottom, which of course is the same, but now I give you the full number. So 7.5 divided by 2 is 3.75. And now when I go to populate my table, I have to be careful because x tilde I is 0, right? Because the distance in the x direction from the centroid to the origin of the coordinate system is 0. Like there's no movement to the left or to the right, or no distance. Whereas for the y direction, this is very different. I'm looking from this centroid location of the individual shape to the origin of my randomly chosen coordinate system. So that distance is not just 3.75. In fact, it's 3.75 plus 1. So that is very important to understand. So 3.75 plus 1, and together that makes it 4.75. Sorry. And now we have all the values for shape A1. Let's next look at shape A2, and you already see that it's also a rectangle, therefore there must be a centroid location right there. And once again, it coincides with my y-axis. That means in the x direction there's 0 distance. Accordingly, my x direction here is 0. And my y direction is 1 divided by 2, which is equal to 0.5. Last but not least, I of course have to calculate the area. That is something we all can do. So that is 6 times 1, and that is equal to 6 square inch. And once again, because it's the first time we're really doing these problems, so the distance from the centroid of the individual shape to the coordinate origin. And so it's 0 because there's no distance in the x direction, but it's 1/2 of the height here of 1, because from here to here it's 1/2. Let's move on to our A3, A and B, and I simultaneously will draw these in there. So let's say there's a centroid location right here. Remember, like 1/3 and 2/3. So 1/3 and 2/3, or in this case, both times 1/3, but 1/3 from the heavy side, 2/3 from the light side, 2/3 from the light side. So my A3A is, first of all, the area is 1/2 base times height. Base, be careful now, because the base is only 2.5. It's not 3. 2.5 times 1.5. And that calculates to be 1.875. 1.875. Again, be very careful, because here we subtracted 1/2 inch from the base, right? So common mistake in an exam is that students take the 3 inch here, but in reality you have to subtract the 1/2 inch. So that makes it 2.5 times 1.5, 1/2, because it's a triangle, and you end up with the 1.875. Now, more interesting maybe is to find the x direction. So this now has to be calculated because, if I may remind you, that we are now looking for the distance from here to here in the x direction and in the y direction. So in the x direction it would be this distance, and in the y direction it would be this distance. Put that into numbers now, and we do that in our table here. So, and I think we can still see what's going on there. So for my x direction first, I have to take the ½ inch, so 0.5, because that's half the width of the middle piece of A1, plus, so sorry, in this case it's actually negative, right? We're talking about the piece here on the left side, so I'm going from here to here, so that's negative. So minus 0.5, and I just put it in brackets, so plus the 1/3 times 2.5. So 1/3 times 2.5. That is my distance here. And that distance happens to be negative 1.33. Okay, now for the y direction, it's similar, but now I need to look from the bottom to here. So that's the 1 plus the 1/3 of 1.5. So let's put that in numbers. So I have plus, in this case, 1 and plus 1/3 times 1.5. And that happens to be equal to 1.5. All right, so now we can do this for the second shape, which of course the area content is the same. It's 1.875. My x tilde now goes to the right side, so let me show you that. Now we're going from here to here in the x direction, so in the right side. So therefore we'll have the same numerical number here, but it will be positive. So let's make that positive 1.33. And in the y direction, it still remains positive, right? So both of them were positive, so plus 1.5. And now we have calculated all the numerical values that we really need for this. And in fact, I'm gonna now draw a vertical line through my table here, because I wanna explain to you that everything to the left of this line is observational, right? So everything here is from observation, whereas everything to the right, you do calculations, right? So everything on the right side is really only plug and chuck, and I can calculate that for you real quick. So obviously xi, which is 0, times the area is 0. Here the same thing, 0 times something is still 0. And then I multiply these values, and I'm gonna fill them in for you real quick. So here I have 0, 0, and my 2.5 here, and 2.5 here. However, be careful, one of them of course is negative, right? So my first one was negative. And so if I have a summation line underneath this, because I'm done with all my shapes here, then I can say that the summation here of this column, so I'm going to make a summation column, that is 0 here. And this is actually the reason, this 0 here is the reason why we were allowed to say that we use symmetry to claim that x bar is equal to 0. So we kind of proved it here. However, for my y bar, that will be different. There will actually be a value here. And so let's fill in the blanks here real quick. So my 7.5 times 4.75, that's 35.625. So 35.625. And by the way, notice that this is in inch to the 3, right? And now my next area, that was 6 times 1/2, that's easy, that's 3.0. And then 1.87 times 1.5, right? Is that correct? Yes. So that's 2.812. 2.8125, if you will, and then 2.8125. And when I sum all that up, I end up with 44.25. And again, this is an inch square cubed. And by the way, just to be clear, this here also would be an inch cubed, right? Don't want to keep any information away from you. So now I have this summed up. I need to do one more computation, right? I need the sum of my AI. Where do I get that from? Here's the area. These are my AI, so all I have to do is sum this one up. So let's do that. If I calculate that, I will end up with 17.25. And now let's look at our formula. What do I really need? I need my AI here. So I pretend that's this value down here. And my summation of yi AI, that's what I find here on the bottom right in this case. So ultimately, I end up with a formula that says 44.25 inch to the cubed divided by 17.25 inch squared, and that results ultimately in 2.565. 2.565 inch. And that is a result and the one we were asking for. So last thing I now have to do is pretty much put that into my sketch, and the 2.565 does make sense because it is very bottom heavy, that shape. So let's put it in here. So 2.565 would be somewhere here, is really where that centroid location is. And to communicate my understanding, I have to draw that in my figure here. So I'm going to draw from here to here. And then I have this distance from here to here, which is y bar, which is equal to 2.565. And notice that I also have a second information now in this picture, and that is the distance to the top, which would be equal to the distance from here to here, if I can get my ruler aligned. So in this direction. And that would be equal to 8.5 minus 2.565. And you may ask yourself, why is he showing us this? But often the problems ask you for the distance either from the bottom or from the top. And it really doesn't matter what you, like how you start. I could have, for example, put my x-axis here on the top, and then I would have calculated my equations differently with different values, but I would have found pretty much this number, whatever comes out of this here, right? So what I'm saying is, it doesn't matter what you calculate, as long as you know the reference to it, you can always deduce your other values. And I believe that kind of sums up the entire problem. I will say though, yes, this tabular method here does make sense for larger shapes. I think for a shape like this is a complete overkill. I showed it to you here for educational purpose, and hopefully you can make the best out of it. And my experience is that students like it because they can just plug and chuck. However, I think on an exam, for example, you spend too much time doing this rather than just fulfilling the formula. So like this, for this shape, I think I could have been faster, maybe by half, if I would have just fulfilled my formulas. However, if I have a shape that is made of many different, maybe 25 different shapes, then I would struggle with just filling everything into the formula, and then I would obviously try to structurize my approach and maybe even use a spreadsheet program. And I encourage you to maybe try one of your homework problems with a spreadsheet program. And please understand that your spreadsheet program is very smart in the sense of computation, and it can calculate many values for you. However, this part here really depends on the engineer. So you have to submit the right values here. And that can be very tricky sometimes. For example, you can easily overlook this ½ here, or you can confuse 1/3 with 2/3 and so on. So that requires some practice. And I invite you to do that. However, let's take a look at the last problem in this lecture series, and then I think you'll have all the tools you need to complete your own homework and to really understand how to solve these centroid problems for composite shapes. So here's another problem which I will not really solve for you. I leave this up to you. It is very similar to what we've done before. I just want to give you a few hints for this. So number one, let's look at what you need to find. So you need to find X bar and Y bar as always in this lecture. And also you want to understand that there's a hole here with a diameter of 1 foot. So before I continue to talk about that, let me give you the answer to this problem. So X bar in this problem actually happens to be 2.11, and in this problem it happens to be feet, and Y bar happens to be 1.34 feet. 1.34 feet. And now what you need to be careful about, so the circle has to be subtracted, and then here is a semicircle, and that semicircle lays on the left side of this coordinate axis of the y direction. So that means everything here on the left side has to be subtractive if you considering this your origin, similar to the problem that we solved before, right? And then also the circle has to be subtractive, but that one has a complete center. So it's a complete circle which has its center right on this axis, so your distance there will be 0. And I let you play with that. Just one last thing I need to tell you, and that is that you have this semicircle here. There's a semicircle here, an entire semicircle, and that you need to know how to find the centroid location for that, right? So let me just give you a hint for that. So for a semicircle, let's pretend it looks like this. So let's say there's a centroid location right there. Of course, you know already that like for a semicircle in this direction, let's call that y bar or y tilde would be equal to r, right? Because r is effectively this distance here from the center of that line to any point on that circle. So we'll call that r. But the distance that you probably have never seen before or never calculated before is actually this distance from here to here. And again, you can find this on the internet or in tabulated like books or mechanics books and any mechanics reference. But for your convenience, I will tell you that this distance can be calculated by 4r divided by 3 pi. And that is the centroid distance, in this case, x tilde for a semicircle, right? So let me show you that like this. So this is the formula you need to calculate that, and I really encourage you to do that because it will help you to be prepared for the exam. Because the things that I usually expect my students to do on the final exam is to have the formulas for the very simple shapes in their head. Of course, for rectangles, for triangles, and for semicircles. All right? And everything else, for example, parabolic shapes or trapezoidal shapes, those exist, but they would not come on the exam without any warning. So what we can say with confidence is that these you have to know for the exam. Know for exam. And what I mean by that is you need to know how to calculate A. You need to know how to find x tilde I, and you need to know how to find y tilde I. And later on, after the next lecture, you also will need to know how to find ix and iy. But that is something we will talk about during the next lecture. So for now, the things that you need to focus on is these three guys for these known shapes. Everything else exists. And if I put anything else on an exam, I would, of course, add the information or these formulas, just like I did here. I would provide these formulas then if I go beyond these shapes on the final exam. All right, so I think with that you can solve this problem, and I believe we conclude the lecture here.